Find the maximum deflection in the beam, in inches. In this problem, beam AB is connected with a pin connection at joint A and a roller connection at joint B. A continuous load, W, acts along the entire length of the beam, and a point load, P, acts at the midpoint of the beam. The beam is made of steel, and the cross-sectional dimensions are provided. The maximum deflection of a simply supported beam occurs at mid-span if the point load is at mid-span and the continuous loading is centered along the beam's length. The maximum deflection in the beam is caused by the point load equals the point load, P, times the length of the beam, L, cubed, divided by the quantity 48 times the Young's modulus, E, times the area moment of inertia, I. The maximum deflection in the beam caused by the continuous loading equals 5 times the continuous load, W, times the length, L, to the fourth power, all divided by the quantity 384 times Young's modulus times the moment area of inertia. Since the maximum deflection from the point load and continuous load both occur at mid-span, L over 2, the property of superposition states the maximum deflection for these combined loads is the sum of the deflections from each load. From the given data, we already have the point load, P, 200,000 pounds force. The length of the beam, AB, is 144 inches. And Young's modulus for steel equals 2.9 times 10 to the 7th pounds force per square inch. To calculate the area moment of inertia, we'll need to consider the cross-sectional dimensions of the beam. The area moment of inertia is always positive and can be thought of as the beam's resistance to bending. The area moment of inertia for a rectangular shaped section about its own centroid equals the base times the height cubed divided by 12. Beam AB can be thought of as 3 separate rectangular areas, with area moment of inertias I1, I2, and I3. To calculate the area moment of inertia for a cross-sectional shape which is not about its own centroid, the parallel axis theorem is used, where A is the cross-sectional area and D is the perpendicular length between parallel axes. So our equation for the area moment of inertia for beam AB is the sum area moment of inertias about the centroidal axis for all three parts. If we calculate I1 for area 1, the centroidal area moment of inertia equals the 12-inch base width times 3-inch height cubed, which equals 27 inches to the fourth. The area, A, for area 1 is the base times the height, or 36 inches squared. Next, we'll calculate the centroidal axis of area 1 and the centroidal axis of the entire cross-section. If we assign a datum of y equals 0 to the bottom of area 3, then the centroidal axis for area 1 is the 3-inch height for area 3 plus the 8-inch height for area 2 plus half of the 3-inch height for area 3, which equals 12.5 inches. The centroid for the entire cross-section is the average of all centroidal axes weighted by their area. Plugging in the appropriate values, the centroid for the entire beam, y sub c, equals 7 inches. Therefore, the perpendicular distance between the centroidal axis of area 1 and the centroidal axis of the entire beam equals 12.5 inches minus 7 inches, or 5.5 inches. This makes I1 equal to 1,116 inches to the fourth. The moment area of inertia for area 2, the web, is calculated the same way and equals 128 inches to the fourth plus 0, since the parallel axes coincide with each other. The area moment of inertia for area 3 turns out to be the same for area 1, due to symmetry. The area moment of inertia for beam AB equals the sum of parts 1, 2, and 3, which equals 2,360 inches to the fourth power. If we plug in the value 2,360 inches to the fourth power for the moment area of inertia, and plug in the other variables for point load, continuous load, beam length, and Young's modulus, the maximum deflection, Y max, equals 0.264 inches. When reviewing the possible solutions, the answer is D.